Hello everyone. Welcome to episode 29 of the Warsaw Quantum Computing Group meeting. Today our speaker is Michał Oszmaniec from Polish Academy of Science, and he will give a very interesting lecture using fermions to attain quantum computational advantage. So before we start, I would like to thank our strategic partners, Narto and Codec, for supporting us, as well as our honorary partners for helping us in advertising, promoting this event. And maybe just one more announcement. I know that at least some of you also heard about the Keywords, a Keyword project, a Keyword initiative. It's an international initiative supporting collaboration, education, and research in the domain of quantum computing. And currently, we are looking for interesting research projects that can be submitted for the Q-Intern project. And later there will be call for interns. So if any of you is interested in just proposing a research project for some potential interns from other participating countries within Keyword, then feel free to do it. There is still about 1 week. So we invite you to do it. And I think that now I can stop sharing my slides. So Michał, first of all, welcome. Thank you for accepting our invitation. It's our pleasure to host you here. And the Zoom is yours. We are looking forward to your presentation.
Thanks, Pavel. Can you wait?
Yes, we can see your screen now.
Okay. Now, can you see my slides?
Yes, we can see your slides.
Let me just minimize how it works. This. Okay. Welcome, everybody. Thanks a lot, Pavel, for inviting me and for giving me a chance to present this work. So it's going to be a lecture about how we can get quantum computational advantage or supremacy with fermionic systems, and it's based on joint work I did with Ninat Damgian, that used to be a postdoc in my group, Mauro Morales from University of Sydney, and Zoltan Zimboras, who is my longtime friend and collaborator from Wigner Institute in Hungary. We posted a paper a few months ago on Archive. You can go and check it out. Right, and maybe before I gave once a talk in Warsaw Quantum Computing, Warsaw Quantum Computing Group meeting, but it was over 2 years ago, I believe. So I just introduced myself. Who am I? So I've been working in quantum information and quantum computing for quite a while. Over 7 years ago, I did my PhD in Center for Theoretical Physics in Warsaw. Then I spent some time as a postdoc in Institute for Photonic Science in Barcelona. Then I came back with my own grant homing given by Foundation for Polish Science. And I spent over 2 years in University of Gdańsk in National Center for Quantum Information. And starting autumn 2019, I'm leading my own research group focused on theoretical quantum computing in the Center for Theoretical Physics. And if I were to summarize my path as a researcher, I moved from mathematical physics, to quantum information, and now I'm doing, let's say, with my colleagues, of course, quantum computing or theoretical quantum computing, if you wish. Right, here are people that constitute my group. So we have Adam Sawicki, who is a senior researcher. He focuses on mathematical aspects of quantum theory. Daniel McNulty is a postdoc that actually is just starting his position tomorrow, and he focuses on measurement theory. and Filip Maciejewski, Zuzanna Kalegari, and Tomasz Batecki are PhD students working on various cool stuff. They're actually in the audience, so we can go and ask them questions, perhaps. And we have also.
Hello, everyone.
Oh, Filip, hello. Yes, you guys constitute a huge body of the listeners. Okay, and we have also Oskar Słowik, who is not my PhD student, but PhD student of Adam, but we collaborate on various topics. And what else? A bit more of advertisement. So yeah, so we are a part of this project TeamNet, Near-Term Quantum Computers, Challenges, Optimal Implementations, and Applications. So as you can see, we work on a variety of topics, certification of quantum devices. So we want to, let's say, we want to test how well devices perform in the presence of noise and imperfections. Also, we are studying, let's say, original limitations of quantum speedup. We are in this NISQ era, so we want to learn how to use NISQ computers to the fullest. And actually, we do more like theory of quantum computation, not real applications. So like we apply our, let's say, techniques to other topics in quantum computing, like hidden subgroup problem or quantum pseudo-randomness or complexity of quantum states or gates. But perhaps like, I underline like the main, let's say, our research like topics. So efficient description of readout noise, error mitigation on NISQ. And like that will be the subject of today's lecture, Bosonic, for like how you can get quantum advantage or quantum supremacy with indistinguishable particles like fermions or bosons. Yeah, and bold advertisement. Like I'm currently looking for a postdoc / quantum software engineer that will be who can join my group. The deadline, the subject is characterization and error mitigation on these devices. The deadline is in 10 days or so. Please email me if you are interested. Okay, with that out of the way, let's move to the subject of the lecture. Right, so just short introduction to this near-term quantum computing. So we all know that like currently we have better and better devices, but they are noisy, imperfect, and not yet scalable. And one can even say that, you know, like if you were to implement complicated, like serious quantum algorithms that people know they work, like Scholl algorithm, it's basically a science fiction to implement them using current hardware. So this is a paper from 2 years ago, I think, that kind of studied, it's a snapshot from that paper, that studied like resource requirements to factor like 2000-bit number, okay, using Scholl algorithm, and they did a lot of optimization. Okay, I just want to point, and maybe it's not state of the art, but close to state of the art. That is what is publicly known, and for like for quite modest, let's say, like by assuming like very small error rate for the whole device, like here is your estimate in millions, how many physical qubits you need to have, okay? Right. So still, yeah, I mean, we are nowhere there, of course. Still, we would like to use those quantum computers for something maybe useful, maybe not useful, like for yes, and I mean, we have high hopes in that, of course. And right, so I want to draw your attention to one particular approach, which I think, like people describe it in like many times in this meeting also, namely variational quantum algorithms. So in hindsight, the idea is to delegate. Well, you have some optimization problem. Let's say you want to minimize value of some Hamiltonian or some energy that encodes some let's say difficult problem, and you do it in the following way. You start with some simple states, then you hit those states with simple, like relatively simple parameterized circuit, like this one, for example. Okay, so it's relatively, it's not very complicated circuit. It has like a maybe bounded depth, depends on some parameters, theta, and what you do, you measure this like state that comes out from this device, and then you do you feed, you measure it, you estimate your energy, and you feed your results to classical optimizer that is supposed to update your values of theta, hoping to get better and better energy. Okay. Right, and like if you start with classical Hamiltonian, namely Hamiltonian, if you have classical Hamiltonian, namely the Hamiltonian which is diagonal in the computational basis, then you end up solving some combinatorial optimization problems like max-cut or max-2-sat, or like you can also, like in physics, you might be solving like approximately ground states of spin glasses. While interestingly, if you have quantum Hamiltonians, that is like Hamiltonians that cannot be kind of presented in like without much effort, without great effort in computational basis, then we are solving some truly quantum problem. Like example can be quantum chemistry, if you want to find like ground state of some molecule. Okay, and yeah, I just wanted to point out why that people are actually implementing those. People are implementing those things in the lab already. So just last year there were 2 nice experimental demonstrations of those variational quantum algorithms by the team of Google. So they did QAOA, so classical Hamiltonians for example, max-cut. And they also did proof of principle quantum chemistry experiments when they were doing like Hartree-Fock, like optimization of, like hoping to get like close to ground states of some molecules. Okay, so the reason why I'm bringing this up is that actually our proposal hardware, it's a bit of like foreshadowing, or actually you will be using basically the same layouts that those papers are using. So by the way, I should say, okay, I was supposed to prepare this lecture in a kind of pedagogical fashion. Let's say I don't think that I fully succeeded. That is to say, compared to my usual talk about the subject, I just added lots of content, maybe on some, like, say, easy level. Okay, so hoping that you guys can then grasp more, but really feel free to interrupt, ask questions. I prefer this to be more like a conversation than just me talking to you for like an hour. Okay.
Hey, Michał, so maybe there's just one question on our chat. Can we ask a question?
Sure.
Okay.
Should I open it?
No, I can read it. Yeah. So at least we can try. There's this question is from Manan. What's the difference between fermion and transmon? I'm not sure how exactly relevant it is to what you have to say, but
okay. Well, okay. As far so fermions are those like fundamental let's say, constituents of matter together with, let's say, bosons. I will be talking about them a bit later, whereas as far as I understand, transmon it's a technical term that refers to particular way qubits are realized in a type of superconducting devices. Okay, right. So people refer to like transmon qubits. So So
Okay.
there is some on there, but like I mean there are like different beasts completely. Okay.
All right. So are there any more questions to Michał at this stage? If not, then I think we can go on.
Okay. So that I was telling about VQE now, but let's switch gears and move to quantum computational advantage, such supremacy. So this is a different paradigm, which aims to the aim is to construct, engineer some problems for which restricted purpose computers could offer speed up, but those problems, they don't need to be practical. And typically those schemes, they come in the form of sampling problems. Okay, typically schemes that are in the market. Not all, but most. So the idea is that you have a quantum circuit V that you initialize in some way, and then it undergoes a measurement, let's say, in a computational basis. And as a result, your device is sampling from some probability distribution. But now, your task is to program classical computer in such a way that it will be sampling from some other probability distribution that will be approximating this probability distribution generated by a true quantum device. And we have two notions of errors here. First is relative error, in which this classical sampler that, recall, it samples from this probability QX, has a property that for every outcome, like the difference of the two probabilities is upper bounded by like some constant and the probability that you wanted to approximate. So it's a very strong notion of approximation. It's called relative error. Another notion is based on additive error, in which you want your figure of merit is total variation distance between two probability distributions. So you can write simple looking formula for it. You have a sum over all the outcomes of moduli of difference of two probabilities. The catch is that it's an exponential sum, right? So this quantity characterizes statistical distinguishability of two probability distributions. Right. And before I talk more about those guys, let me move. Okay. So yeah, the possible advantages are that you can have small technological requirements to realize them. Hardness, I will be commenting on that later, is based on complexity theory. On the negative side, though, yeah, they may not be practical, and noise still can play quite some role there. So let me just now comment on this hardness based on complexity theory stuff here. So in theoretical computer science, people have this assumption or like mental framework that they tend to identify efficient computation with polynomial time computation. That is polynomial, like you will be saying that some task can be realized efficiently on a classical computer if it can be realized on it in polynomial time in the size of the problem. And now we have this beautiful, complex hierarchy of complexity classes in theoretical computer science. You know, we have P class of problems that can be class of decision problems that can be solved in polynomial time on a classical computer. BPP class of decision problems that can be solved in polynomial time with bounded error on a probabilistic quantum computer, namely the computer that can use random bits. We have analog of this class, like quantum analog of this class, BQP, which stands for bounded error quantum polynomial time. So those are problems that quantum computers can solve efficiently, that is to say in polynomial time. And for example, you have factoring here. Yep, you have famous NP class now. That is class of problems that class of decision problems whose solutions can be verified efficiently. And for example, you have tree sat here. You can put here, I don't know, tree coloring also, or plethora of different problems, max to sat also. Right, and then you can people started building generalizations of those classes, especially this NP classes. And you have like the whole hierarchy, whole onion of structures kind of popping out here. Oh, sorry. That culminate in this polynomial hierarchy, which is this big chunk here, which is even further contained in the class P space, namely class of problems that can be solved maybe in exponential time, but using polynomial space. Right, and just very briefly, what is the general structure of quantum advantage / quantum supremacy proposals? So you have some class of quantum gates, epsilon, that operate on some multi-qubit device, let's say, and you start with an assumption that there exists an efficient classical sampler that, if you give it on the input V from this class, it would sample outcomes from some probability distribution that depends on this V that approximates the target probability distribution generated by presumably by the device in relative or additive error. And then you put quite some mathematics. You'll see that later in the talk, and maybe a bunch of conjectures from complexity theory, and to get the following outcome that like polynomial hierarchy collapses. That is to say, this whole like onion of structures that is here kind of terminates at some point. Okay, let's say to the third level, for example. Whatever, like, yeah. And this is considered in that community to be very unlikely outcome based on years of work experience of many wise people working in the field. So this is like exactly this implication is an evidence that there is no efficient sampler that has those properties. Okay, so it's not something one can prove unconditionally, because it's if somebody comes, like shows up tomorrow and proves that P equals to NP, then those arguments on which this reasoning is based, well, they won't work. Okay, and that, as far as I understand, that concerns like those sampling experiments. I'm talking sampling based quantum advantage proposals that I'm talking about. Yeah. today. Are there any questions or comments to this? It's very maybe, it's not very detailed, of course, what I'm showing here, but okay.
No, I don't see any questions now, so I think that's
We'll continue then.
Let's continue.
Right, okay, and just some classes of circuits for which this was proven, like very early on in 2000s, Terha and DiVincenzo showed, okay, it's much actually easier to prove it for relative error. Okay, so it's easy to show that if you have approximation in relative error, then you have approximation in additive error. Basically, you just sum this equation over the domain X. Okay, but converse is not true. But okay, like if you have relative error, it's possible to show that if you have shallow, that is to say, I think the depth 3 quantum circuits, then it's already hard to have classical sampler that would be approximating in relative error. You have this class IQP, which is a class in which that you first Hadamard it's some class, like we can some resistive class of gates. Okay, you first start with computational basis state, then you apply Hadamards, then you apply anything which is diagonal in the Z basis, some unitary. Then you put Hadamards again and you measure. So it's a restricted class of quantum operations. Still, you can prove hardness for relative error. And then later, there was like a plethora of developments that started with boson sampling. It's a seminal paper from, I think, okay, it was published in, I don't actually, yeah, let's say from 2010, maybe it was earlier, by Ornson and Arkhipov, that showed that it's hard to sample from something that boson sampling generates. I will be talking about that later. Also for IQP, analogous results were proven. And those developments, they culminated in a very nice developments about random quantum circuits. Well, more about that in the next slides. So those hardness results, they concern hardness of sampling to some small additive error from outputs of those circuits. So most of the developments are actually focused on random circuit sampling and boson sampling. Right, and just some historical notes. You have actually these days two main experimental platforms to realize this kind of experiments, namely random circuit sampling and boson sampling. So random circuit sampling refers to a procedure in which you have, let's say, array of your qubits, and that are, let's say, in a rectangular lattice. You apply to it like layer by layer, like family of random gates, kind of acting locally here. Okay, locally, namely respecting, this is like a time axis, and you have you have actual space you have in the perpendicular direction, and those gates, they respect locality of the system. And then you measure, of course. You have also boson sampling. I will be talking about boson sampling later, but the idea is that you have this photonic chip that you initialize in some bosons that enter some modes here, and then they interfere in this big interferometer, and they're then measured in the output. And yeah, as probably most of you know, there were two very nice experimental developments in recent, let's say, 1.5 years. One was first, let's say, proof of principle demonstration of quantum advantage by Google and University of Santa Barbara. They used 23-qubit chip, and the depth they had was around 20. Also, just last year, probably November last year, there was nice experimental demonstration of Gaussian version of boson sampling with 50 up to 70 photons and 100 modes. Okay, by a group of Zhao Pan from Hefei. There's still some issues to those schemes. Actually, you have a no-go theorem that makes it very challenging to efficiently certify that you are actually performing the right experiment if you don't characterize the device and make some physical assumptions. One has to fight with better and better classical simulations that are being proposed by people. And lastly, different schemes have different guarantees for hardness. Right, I will be commenting on that later on. Are there any questions to this?
Okay, let's give some time. I don't see any questions now, but maybe just someone would like to ask directly.
Okay.
Yeah,
so with this introduction out of the way, we move to, I can move to our scheme. Oh, is there? Okay, there was some error of slides, but okay, here is our scheme in the nutshell. Okay, so we have some fermionic circuits that I will spend a lot of time describing it later. Okay, that is initialized in a special so-called magic states that have exactly this form written in a, let's say, qubit language. So you have it's like kind of JZ state of 4 qubits, if you wish. So each of those states you can generate by such a simple circuit. You have many copies of such circuits, of such states. You put them to this fermionic circuit that can be either passive fermionic linear optics or active fermionic linear optics. I will be commenting on that later. And you sample from the probability distribution that you have in the output. And the claim is that the hardness guarantees that we were able to prove about the scheme that I will be describing to you later on, of course, they are comparable to hardness guarantees that people can attain with for example, random circuit sampling. Just here, let's say our main results. So the first two. I will be talking about them. They are the core of our paper, actually, but they are actually quite complex to talk about. So we prove 2 technical properties of this family of circuits, namely the anti-concentration property. I will be defining later what that means, but informally speaking, it means that outcome probabilities are with significant probability over the choice of random fermionic circuit, not too small. We also prove average case Sharpe hardness of outcome probability. So that is to say, we prove that if we take V on average from either passive fermionic linear optics or active fermionic linear optics, then it is sharply hard to compute or even approximate. Oh, sorry guys, my mouse is too sensitive. To approximate those quantities.
Okay.
And lastly, this is maybe the easiest thing to grasp. We give an efficient scheme to certify an unknown fermionic linear operation. Okay, so like you give me an unknown v from this class, and I have a procedure to, like that officially will tell me that oh, this is actually this v from FLO. Okay, so in the rest of the talk, I will be just basically debunking all those buzzwords that appear in this slide. So
just a quick question. Can you
yes.
maybe recall this hash-p hardness, I guess, because I'm not sure if all people are familiar.
Okay, so informally speaking, the class sharp, that's a sharp p is a class of counting. It's not a class of decision problems, but counting problems. So roughly speaking, it refers to problems that are about counting how many solutions you have to NP, to some NP problem.
All right. Okay.
So it's even more. It's much harder than. NP, or much harder than. It's actually, in some sense, it contains polynomial hierarchy.
Okay. So I just pasted a link to the article in Wikipedia about hash-p completeness or hardness, if someone is interested.
Yeah. Right, thanks, Pavel. Okay, so now it will be very pedagogical. So this, we are working here with indistinguishable particles, and I presume that people are familiar with quantum computing, but not always with indistinguishable particles. So it's going to be a little tutorial to that now. Okay, so first start with distinguishable particles that we are all familiar with and we know well. So yeah, something very simple, kindergarten almost, and identical qubits. So Hilbert space that describes the system is a n-fold tensor product of two-dimensional Hilbert spaces that correspond to each particle. States, as you know, they can be written as superpositions over those basis states that are kind of labeled by bit strings of length n. We all know that, right? Oh, what's happening? And we have some class of simple transformations, namely local unitary transformations, in which every particle evolves independently, right? So just for the future, this class of transformations that I called fermionic linear optics, they play analogous role structurally to this local unitary to local unitary transformations. Importantly, like when we have qubits in distinguishable particles, we can address them individually. So we can just measure individually, first particle, second, third, and so on, right? Now,
Michał,
to define.
Can we come back to the question, because there's just one question appeared on our chat. What is IFP complexity class mentioned much earlier?
What?
IFP complexity. I'm not sure if this is the correct name. IFP. Maybe there is a typo.
I didn't use anything like IF.
I also can't recall it, so maybe.
Okay. I'm pretty sure, like I'm like I never. Is it? Yeah, sorry.
So maybe George, maybe you can unmute yourself and ask, because maybe there was a typo in your message on chat, or maybe we just misunderstood something.
I might have not caught it exactly. It might. I don't think it was verbal. It was on one of the slides.
Okay, but it was much earlier, yes?
Yeah.
Okay.
Well, there was IQP maybe.
Oh, IQP. Yes, I'm sorry. Yeah, IQP.
Sure. Yeah. Okay. So this IQP stands for instantaneous quantum polynomial time. So, this is along with boson sampling, actually the first, let's say, class of quantum circuits for which those quantum, like those hardness results were obtained. So can I? So this can I annotate? Okay, I don't use it too often. So you have Hadamard's initially. Okay. So here you have some unitary. I have a stylus, but it would be a mess if I did it with stylus now, because okay. So you have such a structure which this is just diagonal in Z basis. Z basis. It's kind of, you can construct it from like ZZ interactions, Z interactions, stuff. Let's say you can think about something like that. Okay, between different qubits. So this IQP stands for, let's say, you can, okay, formally speaking, it's a class of decision problems kind of built on the top of those circuits, but let's say, let's not overcomplicate things. So it's basically class of circuits that, quantum circuits that are of this form. You Hadamard them initially, you put some polynomial circuit built from, let's say, those gates, acting, let's say, between neighboring qubits, you Hadamard again, and you measure. This is IQP.
Thank you. That gives me at least something to look up and work with. Thank you.
Yeah. It was just an example. Okay, now I'm not an expert in the Zoom. Okay, I just okay.
Okay, if you need any help, then let me know.
No, I think yeah, I'm good. But now I need to. How do I move further? No, I move. Okay, good. Good. So we have those distinguishable particles that we can address one at a time. Okay, it was for qubits, but now to move further, I need to have a slight generalization of that, which is I replace local Hilbert space from two-dimensional, make it d-dimensional, and people call it qubits. So I have n identical qubits. So to differentiate from what I was saying just now, like I don't have bit strings, but I have strings of symbols built on this alphabet that has d elements, okay? And everything else is as it was. People consider some objects like that. Okay, but now when I have n identical qubits, I can tell you about indistinguishable particles. So let's start with bosons and bosons in D modes. So bosons are physical particles that are perfectly symmetric upon exchange of particles. So, but you can, like, if we start from n qubits, we can treat bosonic Hilbert space as a subspace of this n qubit space, which is characterized by the bosonic symmetry. Namely, like when you have bosonic wave function, that is a wave function supported on n particles, when you exchange any two of them, let's say second and the fourth, it has to be symmetric. So like if you act with this matrix of the swap, it's the same particle, it's the same state. Okay, and equivalently, those bosonic states, they are eigenstates with eigenstate 1 of this bosonic symmetrization operator, which is operator that basically averages your state over all possible permutations of objects, of particles. Okay, so it's Bosonic symmetry. And now, when you have those strings of symbols, like two of them, okay, I and I prime, like it's easy to see that when you act with this projector on them, there would be the same if and only if for every, okay, for every mode. So let me call mode like internal state in this space. Okay, so like label that I can have here. So I have in total d possible labels that I call modes. Okay, so for every mode, the number of occurrences of this mode, k, I have k, this nk stands for the number of occurrences of the mode k in the string I has to match number of occurrences of the mode k in the string I prime. Okay, so such a property, but now with that I can define fog and occupation number states that are exactly the states that you get up to normalization when you start to symmetrize computational basis states of the ambient space. Okay? Yeah, so they are called fog or occupation number states. And right, so they are characterized by string of occupation numbers. So this number n1 tells you how many particles were in mode 1. This number n2 tells you how many particles were in mode 2, and so on up to mode d. Okay? Now, we have creation. In this space, we have action of creation annihilation operators that are defined like that. So creation operator corresponding to the mode I increases the number of particles in the mode I, whereas annihilate up to this factor, at least, I mean up to some scalar factor. Likewise, the annihilation operator. When you compose them together, you get operator that tells you like how many particles are in a given mode. Oh, here I made a typo. I apologize. There should be a normalization. So you can write, there is a normalization factor. You can write now all your fog states as strings of products of creation annihilation, of creation operators. Those guys, they satisfy some neat commutation relations like that. And now, with all this terminology and concepts, I can define finally bosonic linear optics, which is a class of transformations that you get from some unitary that acts in the mode space. So it's some unitary like that acts in the space of modes, and you can understand this bosonic linear optics in two ways. So either you can think of just acting on every particle with the same unitary. So remember, we had n particles. Okay, so it's similar to this local unitary transformation. This is option one. Another option, you can view it like how those transformations act on creation and annihilation by conjugation operators. So they just linearly transform them. And yeah, you can compose them from simpler operations like phase shifters and beam splitters. Okay? So this is about bosons. Coming to fermions, it's very similar to what I was saying before with the with the difference that, okay, fermions are not red, but blue here. And that means that their wave function has to be antisymmetric with respect to exchange of particles. Okay, so if when I swap two particles, I need to get the minus sign. Okay, and equivalently, those like fermionic states, they are eigenstates with eigenvalue 1 of this projector onto antisymmetric subspace of n qubits. And in a very similar way, we can define, this computation is like, when I was preparing those slides, I basically put A here. So it's the same explanation as before. We can think about occupation number, like states that are labeled by occupation numbers. Okay. So like how many modes, how many number of times a given mode appears in such a string. So we have those four occupation number states. The only difference compared to bosons is that we are restricted, the occupation number states, they are confined to, they can be either 0 and 1. It's because of this asymmetry. So, if I had two particles in the same, two particles in the same mode, then if I exchange those particles, I won't get minus sign. So I cannot have more than two particles occupying the same mode. Now, just like for bosons, we can talk about creation and annihilation operators. They are like up to this funny factor, they look kind of the same as previously. So we create fermions in mode I, or annihilate fermions in mode I. We have occupation number states. And now there is no typo because n's are confined to 0 and 1. Every fermionic Fock states can be generated from like a state that has no particles by such an expression. And we have anti-commutation relations. Now, not commutation, but anti-commutation. So this is like anti-commutation between, so A and B is just like a AB plus BA. Okay, and right, we have anti-commutation relations for fermions. How do I do it now? And right, right, we can define fermionic linear optics, which is defined in a very similar way as before for bosons. So we again had some unitary that acts in the mode space. We'll lift it to the full fermionic space by this, let's say, n-fold tensor product, or we can understand its action on on creation operators. And yeah, the last slide for explanations of fermions and bosons. So so bosons, they are fundamental particles that have integer spin, and for example, photons are fermions, and they can occupy more than one mode at the same time, and importantly, they exhibit bunching. So what is bunching? It's a funny physical phenomena. So take the Hadamard gate acting on space of modes, and classically, if you put, two states, let's say in the zero state, okay, they will be interfering like independently, and you can there will be independently kind of randomly shuffled either to the left or to the either to the up or down arm. So you have 4 possibilities in the outcome. Now, but if you take now bosons, so you know this line corresponds to one bosonic mode, and you act with such a U on the state. So when you evolve, let's say, this creation operators according to the rules that I gave earlier, you will realize that in the output you don't have events in which particles occupy 2 arms. Only they can occupy only 1 arm or another. So this is called bunching. Bosons like to stick to each other, but fermions, they do not like to stick to each other. They are half-integer particles, and for example, electrons are examples of fermions, and they typically interact. And you have this Fermi exclusion principle; they cannot occupy the same mode, and you have anti-bunching. That is to say, when you put 2 fermions in those modes here, there will be just like this linear optical transformation will be outputting the same to fermions here. Okay, that was introduction, very hopefully low level to fermions and bosons. Are there any questions to this? And I see that I'm a bit behind, running short on time. So can you tell me, Paweł, how much time do I have?
We still have time, no worries. So for sure, yeah, if there are any questions to Michał, then yeah, feel free to ask your questions now. This is a good time, of course. I think we can continue until about 7:30 or so.
Okay.
No worries.
So,
Michał, if you have some other slides that you would like to show, you would like to share with us, then you can also do it.
Yeah, I have. I feel now I can actually move to the results. Okay, that we have.
Yes. So yeah, go on.
Okay, so just rehash of fermionic linear optics. So right, so we'll be working like our quantum advantage supremacy proposal is built in the system of like fermions occupying d modes. So we can have different number of particles. So that's why I put here like a sum of spaces. Okay. We have actually in this space, as I was telling you, like creation annihilation operators. Now there is a bit of a twist. That is like we can define some linear combinations of those creation annihilation operators that are called Majorana fermion operators. So you can think of them as Hermitian counterparts of fermionic operators, okay? Of those annihilation creation operators. So they also have some anti-commutation relations. They are Hermitian, that they can be measured. We'll be using that later. Yeah, we have fermionic Fock states, and just to repeat, class now. Okay, I didn't want to overcomplicate things previously, so I was talking about passive fermionic linear optics. Okay, so this class of linear transformations that I was describing previously is called passive fermionic linear optics, and they correspond to linear transformations of fermionic creation operators according to some unitary that acts in the mode space. Or if you wish, you can think of like having the same U acting on every particle, like depending how many particles you have, okay? And it's a representation of a unitary group in mathematical terms in our space. We also have class of active linear optics transformations that they are like somehow slightly more general than those passive transformations. You can view them as orthogonal transformations of Majorana mode operators. Oh, it should be J here. I apologize for that. Yeah, it's a typo. Okay, but according to now orthogonal transformations, yeah. Okay, you can write like the corresponding Hamiltonian if you wish, that corresponds to the unitary. And they also form a representation, okay, of like those gates. They also form a representation now of special orthogonal group in dimension 2D in this full fermionic Fox space. Now, I told you that those fermions typically interact. So, and in some sense, those classes of transformations that are in the literature called, like, you can Google like non-interacting fermions, and you'll be getting those transformations. Like, you know, here you don't have any interactions in a sense. So, but in nature, often fermions do interact. So to realize that physically, we are going to map this system to qubits. So to realize that, we use Jordan-Wigner transformation, which is a unitary map that maps fermionic modes into qubits. So when I have d fermionic modes, I map it to d qubits. And it's very easy to comprehend. You map, you know, Fox states. You know, Fox states, fermionic Fox states, they are given by strings of zeros and ones, because every mode can be either occupied or non-occupied. So you just map it to bit string that corresponds to d qubits. Okay. Under this mapping, Majorana operators, they are mapped into strings of Pauli operators. Okay, so like, yeah, there is some dictionary like that. Importantly, particle number measurements that I was telling you about, they can be realized by computational basis measurements. And here is a nice thing, because local particle preserving quadratic Hamiltonians, they can be mapped to some local qubit Hamiltonians, okay, that act on just nearest neighbor qubits. Okay. So how to realize our scheme now in a quantum computer? So we use results known from quantum optics. People there, you know, study those beam splitters, phase shifters, and so on, and they know, you know, typically you have some primitive elements that act on just two modes, let's say two paths, and you want to compose those larger elements in a bigger network to realize like a more complex unitary transformation. And you actually, those are like seminal results from quantum optics, but also they actually can be interpreted mathematically in terms of some decompositions of Lie groups. You can you can realize arbitrary unitary or orthogonal transformations as an array of nearest neighbor, let's say beam splitters, or nearest neighbor modes transformations. Here, let's say for either for active or for passive linear optics. Okay, and now if we use this fact that I told you earlier, that you can map those local transformations to local Hamiltonians, you actually can let's say for simplicity, for active fermionic linear optics, you can think of every line here as a qubit. Okay, every line is a qubit. And what you have to do, you have to implement some specific 2-qubit transformations. Okay. Moreover, those schemes, when you think about them, here I have d qubits. The depth is of order d. So we get that arbitrary fermionic linear optical circuit can be realized by a circuit of depth d in the one-dimensional architecture. And importantly, the gates that we require, they are native to superconducting architectures, especially this, for example, I-swap gate. We need to use a lot. And this is the same class of gates that were used by Google in those VQE and QARray experiments I was telling you in the very beginning of my talk. Right. So are there any questions to this?
I don't see any questions.
Okay. Then I continue. So, okay, so this is some pitch about like experimental realization of our scheme. Now, let's say if you show a first result, which is efficient tomography of FLO circuits. In hindsight, here is the scheme. So, okay, we start, let's say, with this active fermionic linear optical transformation. And we are gonna prepare a very particular single separable states. So those states, they have the property that they are all zeros, but on the pth place, you have x plus or y plus. You have 2D of them, because we do it for every p. Okay, so we will be feeding those circuits into those states into V. And now we are measuring. We are going to measure very specific strings of Paulis, okay, that actually correspond to those Majorana fermions, fermion operators I was telling you earlier, okay. And when you write the math, when you work out the math, somehow magic happens, and like by collecting like a lot of statistics from this kind of experiment, like for different values of p, different values of q, you actually uncover. Remember that like active fermionic linear transformation was encoded by some orthogonal transformation, right? That was permuting our modes. So you can then make a statistical inference to get this O. And it turns out that you get it in efficient way. Okay, so you remember, we are working with a system of d qubits. So it has exponential dimension. But despite this, you can realize, when you assume that this V is FLO, like when you run the scheme, actually you can estimate it estimate it to accuracy epsilon in the diamond norm using only this many measurement rounds, so d cubed over epsilon square. So it's efficient scaling. It doesn't scale exponentially with the dimension, which is some property that you would get for generic circuits. And diamond norm is just a figure of merit that it's like a gold standard of distance between quantum channels. Any questions?
No. So I think let's continue. Oh,
Okay. Now, okay, now we move to like the core of our proposal, namely like hardness of fermion sampling. So it is now, actually people in the field, they knew for a long time that if the starting state was free, that is fermionic Gaussian or Slater determinant, then sampling from such a procedure, from fermionic circuit, was easy. And you have some references here. And it's somehow based on this difference that you have between, like in scattering process, between fermions and bosons. Because probability amplitudes for bosons, they are related to permanence of some submatrices constructed from your circuit. And permanence, they are hard to compute. But for fermions, the same scattering process is related to determinants that can be computed efficiently by, for example, just diagonalization. And yeah, it's connected to the bigger kind of thing in complexity theory. You have this determinant versus permanent problem in algebraic complexity theory. Okay, I thought it's instructive to give you this efficient classical simulation. Okay, at least to give you an idea, because people, let me say, I really believe that classical, like knowledge of efficient classical simulations of some subclasses of quantum computations are very useful. Like it's not kind of true that if you only have superposition, you are quantum in a sense. Okay, but like, okay, I can tell a lot about possible applications for. Anyway, just let's dive into this classical simulation scheme very briefly. So we start with like standard fermionic state that just n modes are occupied by some fermions, and we apply some, let's say, passive unitary. And this step is easy because we can just update like every mode efficiently. There is a typo, there should be J here. Apologize for that. Or yeah. So like every mode evolves in this way. It's unitary rotated. Now, so this step is very easy. But now, you know, we have some state that is in exponentially large Hilbert space. Because, for example, when the number of photons is the number of electrons is half the number of modes, it's really exponential. Okay, if it goes to half field. So what do we do? The trick is to sample one mode at the time. So you can, for every probability distribution on some like d random variables that can be simultaneously measured, you have the following decomposition. Okay, when you use Bayes rule. Okay, so but it can be interpreted in the following way. So, like if we can sample from this probability distribution first, and then condition on the value x1 that we got, we can sample from like what is the value of the second node, and so on. If we have this power, then we can sample from this big probability distribution. Okay. So how this stuff is done for fermions? So I have those d modes here that I will be measuring. I evolved my my modes already, and I'm about to measure. So I'm just gonna kind of describe this first step, this first update, okay, for you. So I will be measuring x1, and then I will show actually the post-measured state will be also state of this form. And hence I will be able to repeat my procedure over and over. Okay, so when I'm measuring in mode G, okay, I have to like you can write the corresponding measurement operators in terms of creation and annihilation operators. So when you don't observe a particle, you first create and then annihilate particle, and you reverse for the outcome one. And then, so this mode G, you actually decompose into something which is in the subspace that you already had in your state, and into something which is perpendicular. Okay? So you can view this as like wave functions. So I have n wave functions, and I have another wave function, like some part of it is in the span of my wave functions, some part is orthogonal. Okay? And now, what I then do, I can rewrite my state, my Fermionic Fock state in terms of this guy that is like this G-in and kind of other modes. Okay, so this G-in is some linear combination of GIs. Okay, so and those GIs, they are orthogonal to each other. So what I'm doing, I'm basically changing a basis in the subspace. So I'm replacing one of those guys by G-in, and I then do, I know, how it's called, Gram-Schmidt decomposition of the rest. Okay, and with some maths, you can see that you get the same state, because it's like the Slater determinant just depends on the subspace, actually. And now, with this decomposition, okay, you can actually quite easily act with those measurement operators, okay? So when you detect a particle in this mode G, you just replace this G-in by your mode G that you were observing. But it happens only with some probability modulus alpha squared. You also can have some prescription for the negative outcome, okay? And importantly, all those steps you can perform efficiently on a classical computer, okay? So that gives you this post-measurement state, which is also free fermion state, that you can then plug to this part. And if you were to do this naively, it wouldn't work, okay? Like, you have too much entanglement, yeah. Just maybe also for my students that attend this lecture, I wanted to talk about this. Okay. I think it's described nicely in the paper by Terhal and Di Vincenzo on the subject. Any questions?
Okay. Sounds and looks quite advanced. Are there any from our participants?
Yeah.
Maybe I know that there are still some collaborators from your research group. So Philip, for example, Zoltan was here as well. He's not present, but yeah, maybe someone else would also like to give a comment. Maybe I have just one question here, because unfortunately we'll have to finish soon. But how do you think how this domain may look like in the nearest future, or are there some other interesting similar approaches to show the quantum advantage that seems to be promising for researchers currently?
So can I just comment? Okay, I see that. So, there are. But can I comment on that in the end somehow? right?
Okay. Yes. Okay. Yeah. So if you would like to add something else, then please go on.
Okay, I think I exceeded the time. Okay, guys. So just yeah, I tried to be pedagogical. So now I move to like hardness of the sampling. Okay, yeah, I will speed up now. It will be okay. So that's why we need resource states. Okay, and that changes the game completely as you like output probabilities when you have those resource states. They are actually realized by sum of determinants, not just by determinants. And this thing is called mixed discriminant, and it was proven to be sharply hard. Also, you can use some arguments from quantum computation to show that this is the case. But it's not the end of the story. Those are not known results, okay? Right, right, so just, what can I say? So basically, I just want to, probably I skip the technical part of our results, just I want to emphasize conceptual things. So to prove hardness of, just computation of individual outcome probability is, it's not enough to claim hardness for approximation, okay? Especially with respect to additive error. So what do people do? Like, you have to add in more ingredients, which is the main technical part of our paper, okay? So you start with efficient approximate sampler, and you need to have this property of anti-concentration. And then you use so-called Stockmeyer algorithm to approximate to relative error those outcome probabilities on average within the third level of the polynomial hierarchy. And now, when you conjecture, so within third level of the polynomial hierarchy, you can compute those guys. When you now conjecture that it is actually sharply hard to approximate those quantities to in relative error for like on average over the choice of V from this class, then you get the conclusion, this unlikely one, that polynomial hierarchy collapses. And now, this anti-concentration people can prove sometimes, but this conjecture people are not able to prove, and you can only have a like kind of partial evidence for this conjecture based on average case hardness of approximating those quantities to some small additive error. So anti-concentration for random, it's not established for boson sampling so far. It was not, for random quantum circuits, it was established using approximate 2 designs, okay? But you have support, you can have support for this conjecture for random quantum circuits based on works of Movasag and Bulat. And now, what we basically do in this work, we prove anti-concentration for fermionic linear optics, okay, and we prove average case hardness of approximation of those output probabilities to some small additive error. And yeah, I think, okay, this is just maths, okay? So I just skip through it, okay? Sorry, yes, right, some nice maths, mathematical physics, okay? Sorry, okay. Yeah, maybe I just comment that after our work, there was some nice improvement on the technical level in polynomial interpolation by Bouland, Fermion, and others that kind of applied to our methodology actually improves our result a bit. Okay. Right. Okay. So just those are the conclusions. We propose a fermionic analog of boson sampling, which is based on like sampling fermionic linear optical circuits fed in by magic states. We claim it's experimentally feasible because it's related to architectures that people want to use for VQE. We gave strong hardness guarantees in the form of anti-concentration, of outcome probabilities, and average case hardness. And also we show that unknown FLO unitaries can be efficiently certified. Like we have a protocol for that. Some open problems. It would be nice to have experimental, genuinely fermionic realization of the scheme. Okay, Pavel, you were asking for interesting directions. So there is, I think, need for classical simulation of those fermions, of this fermion sampling. Just last week in my group, we were hosting Stasia Stasic from Facecraft, like for companies that do quantum chemistry on quantum computers. Classical simulation is a big thing, I think. It would be nice to have further verification schemes for FLO. Like you can have Gaussian boson sampling has some applications in machine learning because of its structure, and we hope that there might be some in this Fermion sampling. And currently we are working on to apply the technical stuff I didn't have time to talk about to other settings like boson sampling and Gaussian boson sampling. Thank you for your attention, and sorry, Pavel, for running out of time, apparently. Yes.
That's fine. So I think we have time for maybe just one more question, if there is any, or maybe some comments. The Philip is still here, so maybe you can give some more information. If not, then thank you, Michał. Very interesting, inspiring presentation. I think it might be quite difficult for most of the participants, but we'll see. So anyway, we'll be happy to hear your feedback. Later, we'll send you a survey, so you can also let us know. And if you have any questions to Michał, then also you can contact us or contact Michał directly. So we'll send the questions. Yeah. So I hope that the recording. I hope there was no issue with the recording. So I will stop it now, or no, maybe I will first share the last slides that I have to show before we wrap up. Yes. Okay, I hope you can see my slides now. So yeah, I just wanted to let you know that our next meeting will be hopefully on the 5th of July, and most likely it will be about quantum cryptography this time. Yes, so once again, we'd like to thank our strategic partners, SNART and Codec, and honorary partners. And once again, we invite you to apply and submit your research ideas to the Q Intern program within Qword. Maybe some of these interesting research directions pointed out by Michał, or maybe Michał, you can also apply as a mentor potentially. Why not? So you can find some interest there.
Well, I'm not sure. Like you said, it's very technical. So like, okay, I was thinking actually.
But anyway, yes. So I know you also said at the beginning that you are also looking for postdocs, right? So I believe because yes, currently we are looking for senior researchers, so people like you with great expertise and great knowledge who can be mentors for younger researchers, PhD students, PhD candidates, but maybe also people with PhDs as well. Why not? So I believe that this may be a good opportunity, or maybe some of you would later like to apply to be an intern. So that may be also an interesting opportunity. So yeah, and thank you once again for your attention, for your attendance, for participation. I saw that Przemek has sent a link to a form that you can fill in if you would like to get a certificate. Yeah, so Michał, once again, really thank you. It was really inspiring talk. So from my perspective, it was quite advanced, as I said, but I believe that there were some participants that are already maybe much more advanced. So it was just at the very good. It was maybe it was even too simple for them, I guess. So we'll see. But anyway, I understand that this was a very important research work. So this is one of the reasons why I invited you to give this talk. So we are very happy that we had this opportunity to hear about this research. Good luck with your projects. Good luck with this research. We keep our fingers crossed for next achievements and even better research papers in the future. So all the best.
Thanks.
And we hope to see all of you during our next meetings in July. Thank you once again, and now I will stop recording.